Welcome to Chapter 3, Lecture Note Problems. Let's begin with the first problem. Here we are told that vector A, 175 meters above, is directed at 50 degrees below the positive x-axis, and we're asked to determine the x and the y components of the vector. The first thing that we wish to do is to draw a coordinate system, xy coordinate system. Here's x, here's y, and the vector A directed 50 degrees below the x-axis. We wish to determine the projection of this vector onto the x-axis to get the x component and onto the y-axis to get the y component. So let's see how this vector would project along the x-axis. We start at the tail of the vector and we stop just below or above, in this case, the vector arrow. That marks the x component of the vector. The y component we have to connect. We need to project onto the y-axis, which would be this projection here. But if we keep the magnitude of this projection and its direction, we can move it so that we can form a right triangle. Here is the right angle. Now, using trigonometry and the directions of the arrows that represent the components, we can determine the x and the y components. First, let's say that the vector itself has a length that defines the hypotenuse of this triangle. And so we will make use of the trigonometric functions relating the lengths of each side of the right triangle. We can see that the cosine of 50 degrees is equal to ax over the magnitude a, which I'll simply just write as a. Therefore, ax equals the magnitude of the vector a times the cosine of the angle 50 degrees, of course the magnitude being 175 meters, and that gives us a result of 112 meters along the positive x-axis. In the case of the sine of 50 degrees, we see that because the arrow points downward, ay is a negative quantity, the sine of the angle being the length of the side opposite the angle divided by the length of the hypotenuse, which here again I will just merely write as a. And so the value of ay then is minus a sine of 50 degrees, giving us a component that has a value of minus 134 meters. Now, for part 2, we're told that a displacement vector has a magnitude of 10 meters, and we're asked to identify the values of its components ax and ay when the vector makes the following angles with the x-axis. And the angles here don't appear. However, let's go ahead and I can work out what these angles are. So in part 2, extending the page, we have the magnitude of vector A is 10 meters. The angles for which we have to determine the components are 0 degrees, 90 degrees, 180 degrees, 270 degrees. Let's make a little table here. Angle theta, the value of AX, the value of AY, and a diagram of the projection of the vector. Okay, so let's begin. When the angle theta is 0 degrees, let's come over here and draw X and Y plane. The vector A lies entirely along the axis, and therefore the magnitude of the component is the value of the vector itself. Another way we can do this is take the magnitude of the vector 10 multiplied by the cosine of the angle, which is 0, and of course that's going to give us 1. For AY, take the magnitude of the vector multiplied by the sine of the angle 0, which gives us 0. Okay, when theta is equal to 90 degrees, let's see what the vector is going to look like. Here, again, we draw an xy coordinate system, and we place the vector A so that it makes a 90-degree angle with the positive x-axis, and once again, the components 10 meters times the cosine of 90 degrees, which of course is 0. And for y, 10 meters times the sine of the angle, which is 90 degrees, and that gives us 1. At 180, we can see that the vector will lie along the negative x-axis, and therefore we place the vector A on the negative x-axis, and we get 10 times the cosine of 180 and 10 times the sine of 180, which is of course 0 for the sine and negative 1 for cosine. If we go to 270, we can see that at 270 the opposite will be true. We'll have 10 times the cosine of 270, which is 0, and 10 times the sine of 270, which is negative 1. Let's move on to the next problem. Here, we're asked to consider two vectors, 3i hat minus 2j hat, and b minus I hat minus 4j hat, and we are to calculate the following. Let's start with part A, a sum of the vector A with the vector B. We merely add the I hat components, 3 minus 1 I hat plus minus 2 minus 4 j hat. The result is 2I hat minus 6j hat. In part B, we are told to obtain the magnitude of the sum that we just obtained. In this case here, we take the square root of the I hat component, 2I multiplied by itself, plus negative 6j squared. And of course, we distribute the square to the 2, which gives us 2 times 2 is 4. I hat times I hat is 1, plus negative 6 times negative 6 is 36. J hat dot j hat is 1. So the result is the square root of 40. In the last part, we're asked to determine the direction of A and B. Here we have the angle theta to determine the inverse of tangent of the j hat component, which is -6, and the I hat component, which is 2. Now, a word of caution here is that we have to decide in which quadrant this sum, the resultant of this sum, lies. And if we notice that x is positive but y is negative, that must be in the fourth quadrant. And so here, if we take the inverse tangent of 6/2, let's see, that is going to give us a result of minus 71.6 degrees. Now, we must indicate the quadrant. So if we define the angle counterclockwise from the positive x-axis, we have to add 360 degrees and therefore obtain an angle of 288 degrees. Let's move on to the next problem. Here we consider two vectors. These are three-dimensional vectors, and we're asked to determine the magnitudes of C equaling A plus B and D equaling 2A minus B. So let's begin with part A. Here, C, magnitude, represents the magnitude of the sum A plus B. It's as though C is our resultant. Well, here, what we can see is that A plus B gives us 5I hat, that's 3I hat plus 2I hat, minus J hat, that's minus 4J hat plus 3J hat, and minus 3K hat, which is 4K hat minus 7K hat. Now, in order to provide a solution, we have to take the square root and square each of the components. 5I hat squared plus minus J hat squared plus 3K hat squared. Of course, I hat dot I hat is 1, J hat dot J hat is 1, and K hat dot K hat is 1, and so this yields the result of 25 plus 1 plus 9, giving us a value of 35. In part B, we obtain the vector magnitude D, where D now represents 2 times A minus B. Here, we follow the same procedure. Take 2 times A, which gives us 6I hat, minus 2I hat, so this is our I hat value, plus 2 times 8, minus 8, minus 3 J hat, plus 8 plus 7 K hat. Now we add 6 minus 2 is 4I hat, minus 8 minus 3 is minus 11 J hat, 8 plus 7 is 15 K hat, and again, take a square root, and we obtain 4 squared plus 11 squared plus, which is of course minus 11, the whole thing squared, plus 15 squared. Now remember, I hat dot I hat is 1, j hat dot j hat is 1, k hat dot k hat is 1, so we don't even need to consider squaring of these terms. Here, the result yields 362. Next problem. A snow-covered ski slope makes an angle of 35 degrees with the horizontal. When a ski jumper plummets onto the hill, a parcel of splashed snow projects to a height of 5 meters at 20 degrees from the true vertical. We're asked to determine the components of the splashed parcel parallel to the ski slope and perpendicular to the ski slope. Here, this drawing has not come out very good, so let's go ahead and see if we can make our own drawing. Here's the ski slope. This would be the horizontal of the ski slope. This would be the vertical of the ski slope. So let's call this our x and our y axis. Now, because we have a 20 degrees with true vertical, if this is true vertical right here, okay, and the object lives at 20 degrees with true vertical, what we see is that we have to add the slope of the ski slope to this existing value, which is 35 degrees. And so, in fact, with regard to the sloped ski, the angle is 55 degrees. And so now, if this is the component, if this is the vector A, which represents the piece that flies upward, AX is equal to this projection right here, and AY is given by this projection right here. And so it is that AX is equal to, now notice that it points in the negative x direction relative to the slope, and so it's given as negative A times the cosine of 55 degrees, and that gives us a value of minus 4.1 meters, and AY equals A times the, AY gives us A times the cosine of 55 degrees, and that gives us plus 2.87 meters. This concludes the first part of the problem-solving session for Chapter 3. See you next time.